Okay, so let's start this presentation about the CloudButton project, and it's called Serverless Data Analytic Platform. So let me share my screen and I will introduce you to the toolkit that we have developed in this talk. Petra told me you are a little bit tired, so I want to get you excited about this, and we will try to make it like very interesting for you guys. So, okay, what we are presenting today, it's me, that I am full professor at URB and coordinator of the CloudButton.eu project. Josep Sampé could not attend, so I will present his part. Then Gil Bernick from IBM and Tristan Tarrant from Red Hat. So, CloudButton project. So the CloudButton project is in this big data call. And this is a project where the main technical leaders are IBM, Haifa. It is also Imperial College London. It is IMT in Paris, and it is Red Hat. And we also have some use cases like the European Molecular Biology Laboratory in Germany doing metabolomics, the Hatton Institute in the UK doing genomics, and the Matrix Foundation doing geospatial data. So the main goal of this project is to democratize big data by simplifying the overall life cycle and programming model of big data applications thanks to serverless technologies. So this is a big aim. So CloudButton wants to democratize big data. We want to make it super simple to data analysts that are using the cloud, thanks to these novel serverless technologies. And we are going to demonstrate this in this super big data with high volumes that are genomics and metabolomics in bioinformatics and geospatial data, so LIDAR and satellite data. So these are big aims that we had 3 years ago. And we will show our results after 3 years of development. So why we name CloudButton? And you see this text from this Berkeley paper, this Occupy the Cloud, where this professor from Berkeley said, why is there no CloudButton? And he outlined how his students simply wished that they could easily pass a button and have their code existing, optimized, single machine code running in the cloud. And this inspired us 4 years ago to say, we want this CloudButton. Push the button and have your code in the cloud, unmodified. And here others have followed this inspiration. And you have Tim Wagner in this blog post called the Serverless Supercomputer, telling this, what if every developer had access to the world's largest supercomputer? The cloud as a super big computer. Or this from any scale. Developers want the development experience of the laptop with the power of the cloud. They want an infinite laptop. So why if I could code my laptop, but then have infinite resources in the cloud? And that's precisely what we want to achieve with CloudButton. It seems heavy, but I think we have something interesting to show you here. Well, for those of you that are not very aware of what serverless is, I must say that serverless is a platform. This definition, you can find it in this paper. It's a platform that hides server usage from developers and runs code on demand, automatically scaled, and built only for the time the code is running. You will probably know platforms like Amazon Lambda or Amazon S3 or IBM Cloud Functions and IBM COS. These are serverless services that are automatically provisioned. You don't have to provision their uses. You pay only for the resources you are using. They auto-scale up and down, up, very up, like thousands of cores, and down to 0. And so they are elastic, so they can adapt to your workloads very easily. So these kind of characteristics are super good for parallel programming and parallel computing of big data. Here, I'm showing you why serverless for big data. And you see here 2 interesting plots that we did with our platform. You have here the link. And we launched 1,000 parallel jobs that are compute intensive at the same time. In less than 100 milliseconds, we have 1,000 virtual CPUs processing data obtained from object storage. And what is incredible is you have a lot of computing power instantaneously, and when it finished, it stopped billing you, but also the aggregate bandwidth that you can obtain from these functions to object storage. You can process 100 gigabytes per second. So this is the serverless supercomputer. We can process huge amounts of data very fast. And then what we have done is to create a serverless big data toolkit that it's called Lithops. And we are going to explain it now about this. And I want really you to understand the difference between serverless design and cluster computing design. So you probably know another toolkits like Apache Spark, like Dask, like Rai. They are cluster computing systems for big data, unlike Lithops that has a serverless design. And what is the major difference here? With these cluster computing technologies, you need to statically provision the resources that you need for your cluster. They don't scale fast. So you normally, if you require 5 nodes, you program and configure these nodes. You can, of course, have over provisioning or under provisioning if you don't know the resources that you need on advance. On the other hand, with Lithops and our serverless approach, we do it on demand. We create a cluster of the need that we need in the moment, the entire cluster, and we scale that to 0 in each moment. So this is really serverless, not having a cluster that scales a little or down progressively. We have 0 configuration on the file resources. So a data scientist with no knowledge about cloud and cluster can just program a Python notebook and run applications on top of thousands of virtual cores. Not like here where you need a backend engineer to configure your cluster. So in our case, also it's important, it is data driven. So we automatically provision resources based on data from object storage. In a cluster, you normally ingest, then compute. You load all things in memory and you process it there. So then in our approach, we are very good for some cases of embarrassingly parallel computations, data preprocessing, Monte Carlo simulation. I have many examples here of data management and crunching from functions to object storage. And it is super good for elastic workloads. Gil from IBM, he will show you some metabolomic pipelines that you cannot predict. And if they are very elastic in a cluster environment, they will over provision or under provision, things that they cannot do. Also, the fast startup of our serverless resources make our approach suitable for interactive workloads. Whereas cluster computing is normally designed for batch analytics. So let's go to explain now what is this Lithops thing. So Lithops is the major result of the CloudButton toolkit. This is not a research prototype, guys. We have 4 years of development with research engineers from different institutions, from IBM, from universities. I mean, Lithops is in production now in many environments, like EMBL, banks, Metabolomics, and different companies. So it is, you can use it already now, and it is mature software. Lithops can be defined as a multi-cloud Python computing framework that allows multi-threaded local applications to be scaled to massive cloud resources. So you code normal Python in a notebook, and when you launch processes, it is launching functions or resources in the cloud. So here, the difference is that we don't require any configuration or provisioning. You just say you configure your credentials to your serverless services, and that's all. You can access these resources in this link. It is completely open source, so it's free of use. More characteristics. One is transparency in cloud computing. And what is transparency? Is that we are using identical operations for local and remote resources. This is the infinite laptop. You code a parallel application in Python, but it is scaled transparently to all the resources in the cloud, so it can scale a lot. And this is without configuration of the serverless resources. And also, this is multi-cloud. We want to avoid vendor locking. So the same code that you are running will run in different clouds. And I will show you now all the backends that we are supporting, but you change a very little thing, one import configuration, and your code is changing, running identically in another cloud provider. So we created an extensible architecture to support this, and you will see the list here, it's impressive. We support compute and storage services in many clouds. So we support, for example, AWS Lambda, AWS Batch, AWS EC2 virtual machines, and we support S3. But we also support COS, Cloud Object Storage in IBM, and Cloud Functions or Code Engine, or Azure Functions and Azure Blob Storage. And the list continues here with Google and Alibaba. But Lithops can also run on-premise. So we run on top of Kubernetes and Knative, and we run on top of OpenStack. And as storage, you can use Minio, Object Storage, OpenStack Swift, Redis, Infinifan, Ceph. So you can also deploy this on-premise and combine it with cloud resources if you need them. Lithops, it is very easy to change provider with some minimum configuration files or information that points you to the storage layer and the compute layer that you are using. And only changing that, this simple Python code in a notebook will run when you say, for example, here, pull map. We are launching this function in parallel, and we are calculating something. This P calculation now will run in the cloud with the number of processes that you want. And this code is very simple. The characteristics is that now Lithops code, the main program, will orchestrate all these pool of workers that we use in the cloud, either using serverless functions in Amazon or any other cloud. So it will be transparent for you. An example that I always explain is that in EMBL, before they used Spark, and they had a backend engineer and a front-end engineer. Backend engineer for configuring the cluster, front-end engineer for doing the data analytics. Now, with their front-end engineer, they can create Python nodes with Lithops that run over these cloud resources. And the nice thing is elasticity. In many cases, and Gil will explain that, where your pipeline has tasks of different parallelism, so we have an elastic workload that here I need 5. Then I process this data, I crunch this data, and then I need huge parallelism, like 1,000 cores. I do it. In the next stage, I need 100. This kind of pipeline is very difficult to solve with cluster computing technologies, because if you provision the cluster for 1,000, that is the biggest one, you are over provisioning, because in all these stages, you are wasting your resources. With Lithops, you will create 5, then 1,000, then 100 dynamically. And this is very good where your workload is elastic, or even you don't know the resources that you will need. How does Lithops work? So Lithops, basically, in the phase 1, he takes the classes and variables in Python and transfers for you to the cloud. You don't configure containers or anything. You just code a Python code in your notebook. Then in the background, Lithops use object storage to store this information in the cloud. It delivers it to the function, it deploys, and it runs. We have a storage backend that is the object storage, and we have the compute backend that are the serverless functions or the container infrastructure that you are using. Then each worker of the serverless receives the location of the data, it will retrieve it, it will execute it, and then when the execution is completed, the workers will store the result, and the executor module, that is the Lithops runner, will obtain the final resources that you need. So this is the overall architecture of Lithops, that it's transparent of you because you only see a Python notebook. Lithops is very good design for embarrassingly parallel jobs. So if you want to parallelize something like a hyperparameter optimization, Monte Carlo simulation, data preprocessing, web scoring, a lot of these tasks are perfectly suited for Lithops, and Lithops can do more than that. We have in our webpage a lot of use cases and demonstrations of that. And it's extremely good for big data processing that it's in cloud object storage. So Lithops marries cloud object storage with cloud functions. So you have this serverless supercomputing that benefits a lot from big data stored in this object store. And Lithops is integrating data discovery and partitioning in a transparent way. And this is very important, data-driven. So we spawn resources as needed depending on the data volume. And this is because we have created data partitioner for different formats that, for example, with our APIs, we offer a MapReduce API, a Python multiprocessing API that transparently accepts CSV, text file, genomic data, compressed data, metabolomic data, geospatial data in TIFFs and leaders. And we have created a lot of partitioners. And this is really the powerful part of Lithops. When you execute a map function that processes data in parallel from a bucket in object storage, the nice thing is that you just point to this bucket and you just say, for example, here is the sample hello world in big data, word count. You say here, I want to process my map function over this data location. But if in this data location, you can have 1 gigabyte, 100 megabytes, 1 terabyte, or 1 petabyte, whatever you want to put there. I mean, the code is not dependent, it's not task-centric. We are not telling you how many processes you will need or how many resources. We create chunks automatically from this data that go to the required functions. So the data scientist does not have to bother about the resources. He simply say, I want to process data in this bucket, just launch the processes for me, Lithops. And we are doing that. So this is why we are data driven. You don't have to tell how many processes do you need or configure your cluster. And that's why we are doing this data driven partition. So we have, of course, formats that need preprocessing, like LIDAR or IML set. This we have to launch a previous chunking algorithm to leave it there in buckets. But we also have very interesting on-the-fly partitioners, like for CSV, for text, but also for compressed data. With genomics data, we have nice experiments where you have a lot of compressed data. And because Object Store enables you to obtain ranges of data, you don't have to have the data already chunked or partitioned. You have all the data set in your object storage, and our functions will partition it out automatically, even if the data is compressed, to give it each function the information it needs to operate. So this is super important for many use cases that we are using. As I said, genomic is one of the most data intensive that we are using, but I wanted to explain you here about one special use case, that it's geospatial analytics. Geospatial analytics, it's also using big data obtained from either satellites like the Sentinel European satellite or other sources. In this specific pipeline, we calculated NDVI, that I will explain what is, that it's a calculation of the vegetation index in an area. It's useful to calculate water consumption or wildfire prevention. So this kind of climate change things, we can help to do this with our technology. So, for example, there is some data from Sentinel-2 mission. This satellite is monitoring the land and it's creating high quality images that are available since June 2015. And even Amazon makes it available in an AWS S3 bucket. So this information is public. And we are going to show one example where we are using this information. These maps. So basically, data from this Sentinel satellite is captured in different products, and each product is covering an area of 100 kilometers squared. And each product is including all this information about in different bands about the captured information, like the blue bands, the green bands, the red bands, the vegetation, read edge. Well, I'm not going to give you a lot of technical details about this geospatial pipeline, but you have a lot of information that the Sentinel satellite is giving to us. What happens to this Sentinel data? It is astronomically big. It's very huge, and it is very difficult to analyze this data if you don't have a lot of resources. This is also happening in other environments like genomics. For example, genomics, the data is growing so fast that you cannot have it in your own cluster. The UK Ministry of Health has moved all the data to Amazon S3 and to object storage, because object storage in the cloud is the only platform that can host all these amounts of data. So you need tools to process big data in object storage. And our lithops approach is ideal for dealing with these huge volumes of data in a data-driven way, so adapting to this. So here we also use some optimized geotips that Google is providing. They did some calculations on top of the original tips information. So now the nice thing again is that now Amazon is doing the partitioning for us. So now these geotips enable to split this product in 11 tiles or sub-images. So now we can launch parallel functions for each of these partitions in the geotip. You can also access, this is also public information. And then if we can launch parallel functions for each of the parts of these tiles, we will be able to process dynamically in a data-driven way a lot of data. So here we have the task that we want to accomplish is this Ndvi calculation. This normalized difference vegetation index is well known in geospatial environments. It's a simple graphical indicator that can help us to observe leaf green vegetation. For example, when you are observing fires or climate change or water usage in some zone. To calculate that, we need 2 bands of the spectrum that Sentinel is giving us. And here you have the code. Of course, we publish everything in our website in lithops as open source, and you have tutorials, you have open documentation, and we are going to publish, and we already have, but we are going to publish all the big data pipelines of the project, genomics, metabolomics, geospatial pipelines. We are publishing it in the cloud, so you can use these examples to learn and use it with big data and see how they are working. So mainly, I'm not explaining all this code, probably it's complicated. This goes to a Python notebook. As always, you configure where are you using things. Like, for example, I'm using Lambda here, I'm using S3. And then to access some data. So basically here we have very simple. I have a map function that calculates DVI, NDVI data on this ITER data, that it's the bucket where we have the information. We will compare 2 dates to see the differences between 2 areas using this NDVI calculation. This is the code that goes inside the function that takes 1 chunk of data or 1 part of the image, and it will calculate for you this vegetation index. And as I say, this is data-driven. You don't tell launch 1,000 functions, 100. Lithops adapt it for you because he just takes the information from the bucket and launch the required resources. So here, you, for example, see the output between 2 areas. We calculated in California, there were big fires in the summer. And we could see here before, after, and this calculation in September 2019, September 2021, 2 years after that big fire. We see here all this green that now is not here. We see here some water areas that are not here. And here we plotted the difference between the two to really know what has changed in this time. So basically, what we did with lithops is to calculate the NDVI difference between two dates. We analyzed 18 packages. Here is a simple example for you, studying two bands, and we analyzed 9 gigabytes. We launched 1,000 functions in parallel that could process this data in 20 seconds. So you see here the potential of lithops. And I must say, what are the benefits of using lithops for this? First of all, simplicity, productivity. I mean, you can have data scientists that are not experts in cloud. This is democratizing big data. They create a simple notebook and they run it in their computers. And in reality, when they say map, they are accessing massive information in the cloud, in this serverless supercomputer, and they are launching a lot of compute cores in the cloud that are resolving that for them. So the productivity and simplicity are important. The data scientist, he doesn't need to understand the provisioning of resources because the lithops is data driven, and it is using simple Python code. He doesn't need to learn anything about this, or only understand that data is in the object store and that computing is there. And he can even run it locally to check that he understands it with small data and then run it in the cloud. The other advantage that it's not only simplicity, productivity that are important for democratizing the cloud, this idea of the CloudButton, no? They push a button and you have your local code in the cloud. This is the simplicity of pushing a button, but also the performance, scalability, and elasticity. So, I mean, in which other environment you can run 1,000 parallel cores that obtain data in parallel from the object storage at this speed, and they will bill you only for these 20 seconds of computation that you run. And I must say, performance, this is a scalability. The amount of data that you can process is huge. And the pay per use is very interesting to generalize to other environments. So now Gil is going to show you another interesting use cases like Metabolomics and others, where IBM is using lithops in production. I mean, we have developed during these 4 years this project, and now is well tested. So I finish here now. I gave you a general description of what lithops is, and now I let you, IBM and Red Hat, that are our industrial partners, show how they are contributing and using this platform in production environments. So I finish here. Now it's time for Gil to take the lead. So I stop sharing, and Gil, you can start now.
Okay, so let me share it. Okay, so thank you very much. So my name is Gil Vernick. I am from IBM Research, and I'm going to continue where Pedro stopped. So first of all, just to remind, so lithops fits into many use cases, data preprocessing for kind of machine learning, deep learning, because they all require to do some data preprocessing used for machine learning. Batch processing or all kinds of workloads that embarrassingly parallel, that you can map your workloads into parallel tasks, and then every task executes something, and then they have results, and you obviously can have in multiple stages. So you just run lithops with many tasks, and then your lithops collect all the results, intermediate results, and then you run your calculations again on the results, and so you can have multiple stages. Now, in particular, I'm going to to show you the metabolomics use case we developed in CloudButton and also the lessons learned from it. Okay, so the spatial metabolomics, it's an interesting field of research. They basically know, you provide them all kinds of medical images, and they know they're using some proprietary algorithms, and they know how to detect all kinds of anomalies in those huge medical images. And then they know also how to identify very small regions where those anomalies exist. And so this benefit to understanding health, disease, cancer, or all kinds of other issues. And this is very interesting field with a lot of growing interest. And now, but from computer science, it's also a very interesting use case because it's a pure big data problem. So the process, when they run those algorithms to detect anomalies, so this process consider every pixel as molecules, and then they have thousands of molecules in a pixel, and then they also know how to shift those molecules. So eventually, this process of processing those medical images generates huge amounts of resources that you need to run those algorithms. And so you obviously can't run it on your laptop, or you can't run it on some good cluster. So it's very challenging how to make it efficiently. And the use case we work was the Metaspace use case. It's Alexander's team from EMBL that they developed a tool that they call imaging mass spectrometry application. And this application works like this. So a customer uploads a medical image, and then he chooses some molecular databases. It might be one, might be more than one. And now there is those proprietary algorithms that they developed, they are running, and they try to identify all kinds of regions in this medical image that have anomalies, what kind of anomalies. So there are a lot of compute resources required here, and it might take time, depends on what type of the image and which molecular databases you choose. And then eventually, when this process is done, so it will generate output of small images that contains regions from the initial medical image. And those small images also try to imply what kind of anomalies the process discovered. And this is how it works on the general level. Of course, there are lots of algorithms and a lot of processing that happens in the data preprocessing and molecular scale. But that's not the scope of this talk. Now, before CloudButton, before we met this team, so they used Apache Spark cluster on top of, and they deployed their application there, and it didn't work well for them. Now, there is obviously nothing wrong with Apache Spark. Okay, Apache Spark, it's a very popular, I'm sure everybody familiar with it. It's very popular big data engine, and you can do lots of things with it. MapReduce, SQL, even machine learning. It also contains advanced capabilities to process all kinds of big data workloads. And Spark is a cluster. So if you decide the size of your Spark cluster, then it's very easy to install Spark on this cluster, and then you can use it for all kinds of big data workloads. But the challenge with Apache Spark in the Metaspace use case was that they also had many proprietary algorithms that they had to run. So they had to run a lot of software stack on top of Spark. And once you don't use Spark advanced capabilities that comes with Spark, but you only use Spark to deploy your proprietary code, then Spark became a bit less optimized for this. And it may lead to all kinds of issues like less optimized RDDs in Spark, and then they have byte dependencies, and maybe they're meti shuffle, and there are lots of broadcasts. But in particular, a challenge for the metaspace use case was that they actually never knew what size cluster they need. So the normal way you work, you start your Spark cluster, then you deploy the workload, then you run it, and you finish. In case of metaspace application, they never knew in advance how much resources they need, because the algorithms also generated data during the algorithm's execution. So it's not enough to see the input size of the medical image and the input size of the molecular database to figure out what Spark cluster you need. But basically, you need to start running their workloads, and only in the middle of the execution, you will know what size cluster you actually need in reality. But that was too late, because you already provisioned Spark cluster, and this resulted in less optimized way metaspace worked. So either you provision Spark cluster, but then in runtime you realize that the Spark cluster is too large, so you pay more, it costs you more than it actually needed to be. But even worse, if in the middle of execution you realize that the Spark cluster is small, then it's a bigger problem, because then the workload became very slow. It may run hours and hours, and then it may even collapse at some point. So, so the challenge here was how to know what exact resources you need in runtime, how to dynamically provide them you in runtime versus starting some cluster before and then just hope if this cluster will be enough for your workload. And this is exactly what we addressed with LeetOps. Now, so they didn't have to rewrite their application, but they just had to use LeetOps API to deploy their functions. Now with LeetOps, you don't need to provision any cluster in advance. So the metaspace workload contains about 12 different stages, and each stage contains different sets of computations. It might be one stage when you need 1,000 parallel tasks with 4 GB of memory. And then based on the results of this stage, there might be second stage needs only 100 tasks with the 4 GB memory. Then maybe it needs more, and so on. So every stage generates some results, and the second stage knows how much resources needed. And this is exactly how LeetOps provide them those resources dynamically during the execution. So without having limited to a cluster, LeetOps just provision request those resources in runtime, and then it gets deployed the workloads there, run it, then LeetOps collects the results from the stage, and then when LeetOps invoke the next stage, it automatically injects the results from the previous stage. So this is completely transparent to the user. And this is completely serverless. There are no any servers behind. You don't need to keep any cluster, even one machine. It's scaled from 0 to how much you need. And now, so they use it now in production, and they moved from Apache Spark to this architecture, and that allowed them actually to scale as much as they need and also be very cost effective, because now you only pay for the actual resources your workload needs. So, and this is very efficient. Now, LeetOps here use a hybrid approach. So because LeetOps supports multiple backends, so in this case, we use LeetOps use serverless from IBM Cloud Functions, but it also deploys some of the workloads, some of the stages it deploy to fast VMs that we have, next-gen VMs. So LeetOps starts VM, deploy workload, deploy that stage to that VM, then it shut down VM, and then LeetOps coordinates all the how to share results from different stages. Now, why they had to use this VM? Because they have some proprietary code that they just wanted to use it into some huge machine with the many CPUs and memory. And this is very good. I mean, it's still, they have the serverless experience, even it's one of the stages LeetOps deploy a VM for them. Now, I can show you how it works. This is the video, and this is a real video, so I'm going to show you from a VLC. I'm not sure I will run all the video just to emphasize how this works. So this is a Jupyter notebook. And now you as a user, so you choose some configuration, then you choose a molecular database, then you choose your medical image. So here, this is a molecular database, and then you have one up a medical image. And now you begin to run this. Now, we don't need to get into much details what exactly is running here, but you will see now 12 different stages. And for each stage, this dynamically in runtime, LitOps will invoke a number of invocation as needed, and you're not limited to cluster anymore. And then based on the results, the next stage, LitOps will decide how much invocation you need and then how much memory you need. And this is how it works in production. So you can also have, you obviously can use LitOps from your notebooks, or you can use it also from your application if you want to connect it there. So this is an example of the notebook, and the Metaspace, it's another application that they're using. So I can just move it a bit fast, so you will see all kinds of stages here. You see here, LitOps decided on 250x concurrent invocations. And this is just an example. In reality, it might be thousands of them. And then LitOps collects the results. And this is the user experience that you see here. It's all transparent, and there are no hidden things here. This is how it works. So eventually, if you will run this, they will not run it because it takes about 10 minutes to complete these workloads. But then you will see at the end the results of those invocations. It will be exactly those small medical images. Oh, you see here different stages that are created. And now you can see those medical images that are generated. Let's get to them. Yeah, and this is the results that I said before. So when the process completed, you have the small medical images. And what you do with those small medical images, now you can run all kinds of machine learning algorithms on them, because it's already data that was pre-processed from the huge medical image. You got regions of potential interest, and now you can run all kinds of machine learning stuff on them. So now let's back to the presentation, and to summarize this, so it's very cost effective, and this all happens dynamically in runtime, and you get exactly those resources you need. And then you have simplicity of you can use now Python notebooks interactive, and you also may change your application to use it. So you saw, I think, both. It's deployed over IBM Cloud, but there is completely no vendor lock-in because LitOps supports multiple backends, so you can just take it and deploy it into another environment. And you can process now any data sets because you're not limited to cluster anymore. And also very interesting observation here. So now you can also use this Metaspace application on-prem. Now, why would you use it on-prem? Because maybe you have some very sensitive data that you don't want to use over public clouds, but you want to use it inside your organization. So you can take the same Metaspace application from ENDL. You can deploy it with LitOps over Red Hat OpenShift, for example. It's your proprietary. And then LitOps supports Red Hat Data Grid, which is InfiniSpan, so you can use it for fast in-memory sharing of temporary results. And so it's all optimized, and you can switch it just by one line of configuration. You can deploy it over public cloud, or you can deploy it over your proprietary OpenShift cluster and benefit from InfiniSpan integration. So that summarizes the EMBL use case. Another example I wanted to show you, it's the data preprocessing. Now, you usually, when you run in particular all kind of image processing, you usually need to do some data preprocessing on them. So either you do a kind of face alignment, or maybe you need to extract colors. And so when you have the colors, you maybe want to run all kind of machine learning, similarity algorithms, deep learning. And there are a lot of examples over the internet, what kind of machine learning stuff you can run on the images. but now, so let's say I have my business logic to align phase, and then I have my images, let's say, in the object storage. So that's a real example. I will need to run about 500 lines of, I call it boilerplate code. I need to list objects from the object storage. Then I need to invoke my business logic. I need to know all kinds of APIs. It will be slow because I don't know exactly where I need to run this code. Maybe I need to run it over some VM. Maybe I want to run it over my laptop, but then it will be very slow. If I want to run it over VM, then I will need, obviously, to spend time to deploy this code to VM to test it. And also this boilerplate code that only knows how to read images. Now, if I use exactly the same business logic with litops, it will be 3 lines of code. Because I take litops, I point it to my object storage URL, my bucket, and I just tell litops, okay, execute my business logic, and that's it. And then it will be deployed and executed in the cloud automatically, and I don't need to worry about VMs or where to run this code, so and so on. So this is an interesting example I wanted to show you, color identification of images. So I show you how I can deploy it over Kubernetes API. So I want to extract colors, find images by similarity, and to extract colors from those images. So this is another very short video I want to show you. Not this one. And so let's say I use my laptop, okay? And now I have some image in my laptop, and I want to write some business logic code that knows how to extract colors from this image. And then I do some color identification. I got these codes. So now I can extract colors from those images. I test it on my image in my laptop how it works, and I see that it works. I can extract colors and see the color space. Then I write another code that I want to match image by color. Like I say, give me please all images that have specific color in it. And then I test it on my single image in my machine that I want to take images that has a color, I think blue or green. Let's see which color I decided to use here, blue. So, and I got this image. Now I'm done with my laptop. Now I have a bunch of images in my object storage, and I want to run this function now at scale in the cloud because I don't have enough power in my laptop. So I just point it to another backend, serverless. I'm using IBM Cloud Code Engine. I'm using my buckets, Ndvi Calculation collected, and there is 15 images there, and this code executes there. And now I found all the images green in 27 seconds. Now I can run it again and extract all blue color images and so on. So you see the simplicity how I can go from my laptop to the cloud and benefit from all this stuff. So I don't have enough time, but we're close to the end. So behind the scenes, a lot of things happens, and I'm going to get into this, but you obviously need to run a lot of code, boilerplate code, if you don't want to use litops. And that's also the user experience here. So if you want to run it against Kubernetes, you will OpenShift, you will need to do what kind of deployment definition, job description, user application, how to deploy, how to test. But with litops, that's exact user experience you have. You just use function executor, you point it to code engine, and you just run your function, and you get the results. So this slide exactly emphasizes the user experience you have. And to summary what we just saw, so serverless computing, it's a very promising field that but you still need to use the right move there. So to avoid all those complexity, litops exactly address those challenges and makes it also very user-friendly, and yet now you can run more workloads against serverless. And what we developed in CloudButton, it's an open source, so it's exactly designed for this push to the cloud experience, as Pedro described before. We use it internally, IBM. You saw EMBL use cases in external customer. And it also enables all kinds of hybrid use cases over public cloud, OpenShift. And more details, visit CloudButton, and thank you. And I'm done. So I pass it to Tristan.
Thank you, Gil. 1 second as I share my screen. Okay, and here we go. Hello, my name is Tristan Tarrant, and I work for Red Hat, and I work on InfiniSpan, which is an open source project which implements an in-memory key value store. And during the course of the CloudButton project, we've worked on enhancing InfiniSpan to fit into this scalable serverless model that LithOps wants you to embrace. So as I said, InfiniSpan is a mature open source in-memory key value store, and we've made some changes to improve its scalability for serverless workloads. We've extended some of its data structures using Crucial, which is another component that was developed as part of the CloudButton project. I'll describe that in a moment, as well as integrating it with LithOps to enable high-performance data analytics use cases. So we worked on a number of contributions on this together with the team at IMT Paris. And so we had to enhance InfiniSpan's elasticity and scalability. So we achieved that by compiling InfiniSpan, which is written in Java, to native, so as to reduce its memory footprint and increase its startup performance to make it fit better with a cloud model, and introduce a Kubernetes operator so that its management is automatic and transparent. So a system engineer doesn't need to do anything to provision and scale InfiniSpan clusters. IMT worked on implementing mutable data sharing and with high-level abstractions and strong consistency. And this component is called Crucial, and Crucial is an InfiniSpan extension which exposes these constructs to be used in the serverless applications. And we also worked on exploring non-volatile memory support by implementing JNVM, which allows us to have faster access to cold data, so that persistent memory is automatically available after a restart. So this is where InfiniSpan fits roughly in the architecture. Actually, go to the next slide, which goes into a bit more detail. So this is the InfiniSpan storage, in-memory storage running on Kubernetes, of which Red Hat OpenShift is Red Hat's commercial offering. And the InfiniSpan operator manages the provisioning and scaling of the InfiniSpan pods, which have been enhanced with a Crucial library as part of the InfiniSpan stateful sets. And the LithOps clients connect using the intelligent hot rod protocol to the InfiniSpan pods. Hot rod is an intelligent protocol that automatically, transparently supports the scaling of the backend, so that the front end doesn't need to be reconfigured to know that new nodes have been added. So the work that we did on increasing elasticity in order to make InfiniSpan fit better in like a true cloud native experience was to implement new algorithm to reduce the initial transfer of data between nodes. As you add nodes, they need to share some information. And we got some very good results where the startup time was decreased by 66%. And also the being able to process the responses very quickly as soon as a new node has been provisioned. Before was over 4-second delay and before being able to process a request, and now it's well below half a second before the first response can be processed. So a very, very sizable improvement, and something that really fits with the serverless model of rapidly scaling. I will describe some of the data structures for mutable data sharing, so that functions can store data, because functions are stateless by definition, but they may want to share data between different stages. They can use InfiniSpan enhanced by Crucial with a number of interesting, highly consistent, strongly consistent sharing data structures. So, for example, a number of linearizable weight-free distributed objects such as longs, lists, and maps, which are atomic. A number of primitives for thread synchronization, such as cyclic barrier, semaphore, and futures, and the ability to define any arbitrary shared object and persist it across the cluster without any knowledge about the size of the cluster or any other consistency guarantees. Everything is handled transparently. The crucial constructs are available in a number of high-level abstractions. So you can use Java, Python, and even shell scripts to access these. So it is very flexible and should fit any model. By using these mutable data sharing structures, we have performed some interesting comparisons with Spark, where the big advantage was demonstrating that we could get faster performance, and in some cases a lot faster performance thanks to the in-memory approach at a similar cost to Spark. So with two of the use cases that we've tested here, logistic loss and logistic regression and k-mean clustering, we observed significant improvements, and as you can see in the table, the cost stayed virtually the same. And we're nearly running up until the end. So the other big part of the research that we did was integrate the new Optane NVM non-volatile memory, persistent, also known as persistent memory storage, that gives RAM-like performance, but also SSD-like persistence. So which gives the ability to essentially be able to scale down without data loss and scale up while maintaining storage very quickly without having to load it from secondary storage, slow HDDs or slightly faster SSDs. And we've seen performance up to 10 times that of a file using a file system. And this can provide significant improvements to a number of workloads. And since we only have a little time left, I think I'll pass the word back to Pedro.
Okay. Okay, so I will share my screen now. Yes. So, okay, let me just conclude. It will be very brief. I know we are brief on time. So just after the nice presentations from Gil and Tristan, thanks a lot. I mean, they really explain very nicely lithops and CloudButton results. So some takeaways for you. So we had this overall goal that was to democratize big data thanks to serverless computing. Takeaways for you is that lithops is a mature serverless data analytic platform already in production. So this is not a research prototype. IBM, after the end of the project, is maintaining it. There is also some startup being created around this. So it will continue in the next years. The code source is stable, and there will be a lot of use cases and tutorials that you can find there. And even in the next months, you will see more exciting results around it. The nice takeaways is that lithops is multi-cloud. So this memory, this saying about write once, run anywhere, is happening already with lithops. So you write the code once and you can execute in a variety of computing and storage platforms. The democratizing big data is pushing the button is simplicity and productivity. I mean, you just code Python notebooks, and thanks to our data-driven partitioning and provisioning, data scientists don't care about resource provisioning. And this is really useful because you can code your laptop and run it and scale it on the cloud. The other thing is performance and scalability. I mean, you have a huge amount of resources at your hands. It's the serverless supercomputer. You can have aggregate bandwidths of 100 gigabytes per second and launch 1,000 virtual CPUs in less than 100 milliseconds in the cloud. So you can really process a lot of data. And lithops is really optimized for cloud object storage. If you have a lot of data there, lithops will chunk it, will partition it, and will give it in parallel to many computing functions. And the last thing that I wanted to say, and that Gil explained nicely, and also Tristan, is elasticity. I mean, really, in cases where you don't know the resources that you need, or where your pipeline are really elastic, and they have different requirements of data computing, with clusters, you will end up over provisioning or under provisioning. And here you will just pay as you go, run dynamically the entire resource that you need, and finish it and scale to zero. So this is my last message. I don't want to take more of your time. We finish here, and now we open this for questions. So thanks a lot for coming to this presentation. Okay, so we now finished. Any questions? Petra? Or I think in the chat, there are no questions for the moment. Okay. Thanks. You can always access the website. There is a lot of documentation and examples. And as I said, it's mature software that you can already use nowadays. And you can contact us. For example, I'm being contacted by different groups, for example, in genomics. Now in the UK, they are asking them to move to the cloud, and they don't have experience in transitioning to the cloud. Take care with the cloud. You can have big expenses if you are not doing it correctly. So we are optimizing how you process data, so we avoid this kind of problems when you transition to the cloud with lithops. Okay. So, Petra, if there is no questions, I understand that we finished the session. Okay. Thanks a lot for your time.
Thank you very much.
Thank you.